All right, so we left our heroes talking about inertial brakes on zip lines and why you should always be honest when the nice people on the zip line ask you, what do you weigh? Don't lie. You'll die. Lying means dying. So now we're going to talk about the concept of equilibrium. So we said things want to stay in motion or stay at rest. That is their tendency. And now we have to talk about what happens when they are moving at what we call equilibrium, or when they are at equilibrium. So if it's either moving at constant velocity or it's at rest, it's at equilibrium. Basically what this means is acceleration equals 0. Because if you're at constant velocity, there's no acceleration, acceleration equals 0. If you're sitting still, there's no acceleration, acceleration equals 0. Equilibrium is the point at which acceleration is 0. How do we figure that out? We got two options. Best way, I mean, we've got the obvious sort of colloquial, well, we look at it. If it's not accelerating, it's at equilibrium. If the problem says it's moving at constant velocity, it's at equilibrium. If the problem says it's sitting still, it's at equilibrium. But if the problem doesn't say any of that, what if the problem just tells you there's an object, these are the forces on it? How do you find whether or not it's at equilibrium? You resolve all the forces. And as long as the sum of forces on both axes is 0, it's at equilibrium. So this whole time we've been talking about things where we say, oh, well, on the y-axis it's not flying up in the air and it's not dropping, so therefore sum of forces on the y equals 0. What we've really been saying is that on the y-axis the acceleration is 0. We've been saying that the sum of forces on the y-axis equals mass times acceleration, and in this instance it happens to be 0. And then the sum of forces, the sum of forces on the y-axis, oh yeah, well it also happens to be equal to all the forces up minus all the forces down. So the mass times the acceleration is equal to all the forces up times all the forces down. This is one that you probably, you should remember from physical science, F equals ma. This is Newton's second law. I don't care if you remember what's number 1 and what's number 2 and what's number 3. Though 1 is inertia, 2 is F equals ma. I don't have a handy mnemonic because I mix up the numbers all the time. I don't think the numbers matter all that much. What you should know is that acceleration of an object is directly proportional to the net external force and inversely proportional to its mass. So the sum of forces, the net force on all axes, equals ma. And that is a vector sum. So that's going to be at a heading. We remember that acceleration is a vector. Acceleration is going to have a heading. And that force, the acceleration, is going to be on the same heading as the force vector. Okay. The cool part is we can do math problems. So we got Roberto and Laura are sitting across each other on a white table. Laura slides a 2.2 kilogram book towards Robert. Net external force acting on the book is 2.6 newtons to the right. What is its acceleration? Well, this is like total weenie math. This is so stupidly simple. It barely bears talking about. Sum of forces, which we can start calling net force now, because it's sum of forces on all axes. Net force equals mass times acceleration. We have the net force. We divide both sides by mass. We get acceleration. Oh, gee, would they all be that easy? Heck no. So we have 2.6 newtons divided by 2.2 kilograms equals some quantity of acceleration. Let's do a real quick dimensional analysis here. So newtons divided by kilograms. What's a newton? Do you remember? Don't tell me a fruit-filled cookie.
Grams times meters per second.
Yes, it is. 1 newton equals 1 kilogram meter per second squared. So if we're dividing newtons by kilograms, lo and behold, what do we get? Meters per second squared, which seems an absolutely perfect unit for acceleration. Sig figs 2, so 1.2 meters per second squared is the acceleration of the book. Are we done?
I'm guessing no.
I'm guessing since you asked the question. Acceleration is a vector force, yes? What's the heading here? To the right. To the right, to the right. I would probably also accept towards Roberto. Well, you know, given the setup that they give you, Laura slides the book towards Roberto. So the motion of the book is towards Roberto. I don't see that that's...
I thought you just said something right. I was really confused.
No, Roberto's actually in the question. Okay. Let's do something a little more complicated together before I turn you loose. Yes?
Oh, yeah.
Yeah. That was a trick question. Because, of course, we still show the forces as originating from the center of the object, and it doesn't matter if he was pushing or pulling. Now, you know, don't get me started on right and left. I don't really understand that. But we're showing equal lines, roughly, as well as my drawing will accommodate. And initially, we had equilibrium. Now, as they pushed a little bit harder, do you know what happened? Their force vectors, I believe, ended up doing a little bit of this. Because what we saw, and we'll get rid of the initial force vector, what we saw was that the chair, in fact, didn't move. Neither of them, you know, won, as it were. But in fact, the chair started to move this way. Notice that that is not connected to the thing. That is not a force vector. That is a motion line. That's a separate thing. It's not touching the object. It's off to the side. So we had an initial velocity equal to 0. We're not going to try to find, but we know we had some acceleration. So we're going to do some sort of guessing here, or making up numbers and putting them in. So, yeah, that works, you know. So we're going to assume that Brady was pushing at about 15 degrees. Let's see. That's south. Oh, this is all upside down. Okay. 15 degrees front from lab. And Brandon, I think, had a slightly shallower angle. We'll say it was 7.0 degrees front from windows. Well, what's our net? Oh, we need some magnitudes here. So we'll assume that Brady was exerting about 50, I'll put a decimal there, newtons of force. Brandon, I don't know, you were both kind of like shaking a little bit. I'm not sure. We'll say you were pretty closely matched. Well, actually, you know what? You were probably exactly matched. At least you were matched because you were at equilibrium. So let's say you both put 50 newtons of force on our poor hapless victim in the chair. So what was his acceleration and what was the heading? Well, let's do, you know, how do we find net force? We resolve the forces on all the axes. So the x-axis is easy because sum of forces on the x, was he moving on the x-axis? If we kind of square it off and clean up all the fuzz, he was not moving side to side. He started to move. Which way did you move, Dustin? Towards the lab. Shoot. I like the way I've written this better. Okay, so all confusion about what direction things were moving aside, we'll just go ahead with with that. So we can kind of set our x-axis aside because the action is on the y. And we've got a force of Brandon, or force of Morgan and a force of Duncan on the y-axis. So sum of forces on the y-axis, well, is it equal to MA? Yeah. On the y. Is the sum of forces on the y-axis also equal to the force of Duncan on the y? And they're in the same direction, plus the force of Morgan on the y? Yeah. So guess what? This is so cool. We can say that the mass times the acceleration on the y is equal to the force of Duncan on the y plus the force of Morgan on the y. Ooh. You see where this is going, I assume. We can find the acceleration. Hot diggity forces. So acceleration on the y is equal to the force of young Duncan on the y plus the force of young Morgan on the y, all divided by the mass of Dustin. We'll make that mass of Lane, since we're using last names. Okay, so we've got an expression. All we have to do is plug in our expressions. Y'all right there? So force of Duncan on the y is force of Duncan sine 15, force of Morgan sine 7, all divided. We'll estimate Brady's mass, or Dustin's mass at 75 kilograms. So we had 50 newtons here. We had 50 newtons here. And we're going to estimate this at 75 kilograms. Get me an acceleration. Okay, I've got a raw answer of 0.2537 on and on and on and on meters per second squared. I mean, we know he wasn't accelerating very rapidly. That's probably not unreasonable. That's what we're looking at. And we need a heading for that. So based on what I was thinking, I guess it would be towards the front of the room. Obviously, I'm not a reliable witness and should not be called in a criminal trial. I'm much better with directions. So then we would have our acceleration. We could find his final velocity if we continue to exert the same force. We could do all kinds of handy-dandy stuff. Questions, comments? So basically now we've gone from just doing net forces to you've got this MA piece to fit in. So once you find net force, that net force is equal to the mass times the acceleration. All of the 4B problems, those are on, well, whatever page they're on. Oh, wait, 137, 138 probably. All of those, and then I will have the worksheets out for you tomorrow.